are back for the second part of the video lecture for Chapter 15. We're going to start talking about what's called statistical power, or the power of a statistical test here in a moment. But before we do that, I want to quickly review Type 1 and Type 2 errors that we talked about in the first part of this video lecture. Remember that errors occur when we incorrectly reject a hypothesis. So let's say, for example, that our null hypothesis is true. All right. If we collect a sample mean and the p-value calculated from that sample mean tells us that we have a less than, say, 5% chance of getting a sample mean that low, then we would reject that null hypothesis. But if it turns out that null hypothesis is true and we reject it, we have made a type 1 error. All right. That probability is called alpha. It's our significance level that we set beforehand. It's our threshold cutoff for our p-value, against which we judge our p-value, I should say. All right. Now, let's say, however, that the alternative hypothesis is true, and based on our p-value, we, in that case, reject that alternative hypothesis. In other words, the alternative is true, but we accept the null hypothesis based on our p-value. That is a type 2 error, okay? The probability of doing that is called beta. All right, so the power of a statistical test is a term defined as 1 minus beta. So it's 1 minus the chance that we're making a type 2 error, all right? Okay, so another way to put this, and probably the way you should think about this because it's more straightforward and more simple, the probability of rejecting the null when it is false is power. So if we reject a null hypothesis, what is the probability that we are correctly doing so? If that null hypothesis is false and we reject it, what's the probability that we're not making a mistake in doing so? Okay, that's what statistical power is. And there are a number of things that affect this, all right? First of all, the size of the specified effect. The specified effect is the difference between our alternative hypothesis, our alternative hypothesized mean, and our null hypothesized mean. The larger that difference, the larger the specified effect, the easier it is to see, the easier it is to detect. In other words, the closer our two sampling distributions are to each other, the harder it is to see the difference between them. The further apart they are, the easier it is to see that difference, so the higher power we have. The significance level, alpha, affects this, okay? A lower alpha, say 0.01 compared to 0.05, 1% compared to 5%, means you're setting the bar higher, so your power is lower. The sample size, the larger sample, the greater the power we have, because larger samples give us narrower sampling distributions, and therefore it's again easier to see the difference between those sampling distributions. Finally, the population variance. Now, population variance is your standard deviation squared, so you could think of this also as standard deviation, right? The population standard deviation. A larger standard deviation gives you wider sampling distributions, which would overlap more, and that means it'd be harder to see the difference between them. Smaller standard deviation, less variation, more narrow sampling distributions, the easier it is to see the difference between them, all right? That's how you have to sort of think about this. And this R Psychologist website here will allow you to see what changing any of these factors will do to power, all right? So you should play with that. You should go to that website and play around with it. All right, so this is a screenshot from that R Psychologist website. And so what this is showing us is a good illustration of how we should interpret and think about power. Okay, so let's say that we have a population or a sampling distribution from a population, and that's this one here. So we have our hypothesized null mean, 0, whatever that might be, whatever this x-axis is measuring, right? Okay. And let's say that we collect a sample of, say, size 25, whatever, and we get a sample mean. If that sample mean were to fall, let's say, right there, then at significance level 0.05 or a confidence level of 95%, we would, in this case, accept the null hypothesis because it's relatively close to that hypothesized null mean of 0 in this case. All right, remember, if we set our significance level at 95%, we are defining an area under this curve of 95%. So we have a z critical value over here and one over here on a two-tailed test, 2.5% of our area there, 2.5% there, 95 in between. So the z critical value is 1.96 standard deviations away from our mean. And that z critical is how we judge our p-value. So if you get a sample mean with a p-value of, say, 0.15, that's probably because the sample mean falls relatively close to this hypothesized mean. And in that case, your p-value is greater than your critical p-value or your alpha of 0.05, you accept the null. Okay, if the null is true, and you accept the null, you've not made an error, have you? No, that's the correct decision. All right, what if, however, this null hypothesis is true, but your sample mean happens to fall, say, right there, which it could. There's a 2.5% chance of that. In that case, because it's to the right of that z critical value, you would reject the null. But if the null is true, and you reject it because that sample mean fell out over here, you're making a type 1 error. And this red area here, this one and this one, 5% total, is your chance of doing that. It's your chance of making a type 1 error. That's what alpha is, all right? Okay. Now, let's say that our null hypothesis is not true, and the alternative hypothesis is. If the alternative is true, we actually have a different sampling distribution right here with its own mean, 0.63 or whatever, all right? Okay, you collect a sample mean, and let's say that sample mean falls out right there, which by chance alone it could. If that sample is from this population, because the alternative is true, yet it falls to the left of our z critical, we have to accept the null. And so you accept the null because it falls to the left over here, meaning it's part of this sampling distribution. But you're doing so even when the alternative is true. That is, so you're accepting the null when you should have accepted the alternative. That is a type 2 error, right? That's a type 2 error. It's like a guilty person going free. Okay, now, what if your sample mean falls right here again, and our alternative is true? So this hypothesis is true, our sample mean falls there, it's to the right of z critical. In this case, we would reject the null and accept the alternative. In that case, that is not an error. That's the correct decision, okay? Because the alternative is true. All right, what is the probability that we are making the correct decision when we reject the null in that way? It's the entire area of the sampling distribution to the right of z critical. That's your power, 80% in this case. So again, you have to realize that power, all right, is the probability of rejecting the null when it's false. So if this null is false, our sample mean falls to the right of that, the area to the right of z critical is our power. So if that sample comes from this second sampling distribution, a different population entirely, what is the probability that that sample mean falls to the right of z critical on that second sampling distribution? It's the area to the right of z critical. It's 80%. And 80% is typically sort of the standard that we look for, right? Anything below that is kind of considered to be low power. Anything above it is good, okay? It's just a way to qualify our decision to reject the null, okay? So power can be a confusing thing, but if you think about it in terms of these two overlapping distributions here, and then you actually go to the website and you change some of these slider bars, change the significance level, change the sample size, change the effect size, you can see what happens to these sampling distributions and therefore power as you change these things, these factors, okay? And you should do that to help you understand power. All right, so let's look at another example here. So in a previous chapter, we looked at, whether or not poor mothers have smaller babies. Does socioeconomic status, income affect birth weight? National average birth weight is 120 ounces. So we have a normally distributed population, 120 ounce mean, standard deviation of 24 ounces. We want to be able to detect an average birth weight of 114 ounces. In other words, 5% lower than the national average. Okay, so we set our alpha at 5%, okay, 0.05. We have, this is an applet that I need to make sure is up on Canvas, but this is an applet where you can change these things. We have our population mean, hypothesized null mean of 120. We're interested in lower birth weight, so it's a one-sided alternative, less than 120. Sample size 100, standard deviation 24, alpha 0.05. Our alternate hypothesized mean is 114. Okay, so alpha 0.05, 95% confidence. That means we are looking at 1.96 standard deviations below our population mean. That's our Z critical value right there. Our sample mean, or the mean we're looking for, is 114. It's right here, so it falls within this little tail. That tells you need to reject the null. That's telling you that, yes, it does seem that based on our sample that poor mothers do have lower birth weight babies, all right? So the question is, where does that Z critical fall on this other sampling distribution? This would be a sampling distribution for, lower birth weight babies. It falls right there. Mean of 114, Z critical falls there. What's the area to the left of that? 80%. So with our sample mean falling here on the hypothesized null population sampling distribution, we reject that null. What is the likelihood or probability we're doing so correctly? 80%, because that sample mean would fall here, somewhere in here, 80% of the time. Power is 80%, okay? All right, and moving on. Okay, last thing really to talk about in this chapter is the problem of multiple analyses, all right? So if we set our alpha, or our significance level, to 5%, 0.05, that represents the probability that we accept of making a type 1 error, okay? That's our significance level, alpha. We set alpha at 5%, we make multiple analyses, we can expect a type 1 error about 5% of the time. That's the problem with multiple analyses. So if you run a single analysis only, you collect one sample and you calculate a p-value for that, this is not a problem because we accept a 5% chance for that one sample of making a type 1 error. But if we do the same analysis with 100 random samples, each one individually, we can expect 5% of them to result in type 1 errors. We can expect 5 of them to be significant even if our null is true. These are what we call false positives. Okay, you probably heard that in a clinical setting in terms of testing for a disease or a coronavirus or whatever, false positives, right? So false positives do happen, and on a single analysis, we accept a 5% chance of making a false positive, type 1 error. But if you do 100 analyses, or let's just say even 20 analyses, in 20 separate analyses, you have a 100% chance, you're pretty much guaranteed of getting one false positive if the null is true. That's a problem, okay? So as an example, right here, you run a test of hypotheses for extrasensory perception, ESP, on an individual person chosen at random, okay? 5% chance of a false positive on that person, that test, that's acceptable. But you then run the same test on 19 other individuals also chosen at random. What's wrong with that? Every time you do a test like this, you're compounding the probability of making a type 1 error, a false positive. So it's very likely you'll get, one of these 20 people who will test positive essentially for ESP when maybe ESP doesn't even exist. So for a significance level of 5%, you can expect that one individual will have a significant result by chance alone, right? Even if your null hypothesis that ESP doesn't exist is true. All right, another example of this, question of cell phones and brain cancer. Could the radiation from cell phones be harmful to users? A lot of studies have found little or no connection between using cell phones and various illnesses such as brain cancer. Here's part of a news account of one study. A hospital study that compared brain cancer patients and similar patients without brain cancer found no statistically significant association between cell phone use and brain cancer, or what we call glioma. But when 20 different types of glioma were considered separately, individually, an association was found between phone use and one rare form of glioma. The interpretation here is that since the 19 of those 20 types of glioma showed no relationship with cell phone use, but one did, that one was very likely a false positive, okay, because you did multiple analyses. On 20 analyses, you can expect to get one false positive, and that's probably what this one type of brain cancer, the association between it and cell phone use actually was. All right. Okay. We're going to see later on how we can get around this multiple analyses problem. Okay. So everything we've been doing up to this point, at least the past few chapters, are referred to as Z procedures, right? We calculate a Z-score, which is a measure of the number of standard deviations away from a mean that a sample mean falls, okay? Based on that, we calculate a p-value and do a test of statistical inference to determine if that sample was likely to come from that population or a different one. So, the thing about this is that the data has to be a probability sample. So we have to collect the data completely at random, right? Through a randomized experiment or a randomized observational study, whatever. And the reason why we have to do that is because statistical inference, okay, cannot fix basic experimental design flaws. So think about election polling. If a pollster group is collecting information about people's opinions for presidential election or whatever, and they purposely leave out a demographic group, they're introducing personal bias, which might very well bias their results. Calculating a confidence interval or a z-score or a p-value can't take that into account. It can't see that. So statistical inference relies then on collecting data completely at random to eliminate bias. Very important. Second, the sampling distribution has to be approximately normal. Remember, we said that with central limit theorem, even if you have a wildly skewed population distribution, if your sample size is large enough, your sampling distribution will be approximately normal. That's one of the main reasons for collecting as large of a sample as you possibly can, right? The large sample will allow us to apply the central limit theorem, which tells us that from a skewed population, a large enough sample will come from a relatively normal sampling distribution. Finally, to use a Z procedure for a population mean, we need to know the population standard deviation. And in every case that we've looked at up to this point, we have known what that population standard deviation is. But I've also said, as we've talked about this, that in most cases we don't actually know what the population standard deviation is. So how do we do this, right? If you got to know what the population standard deviation is, calculate a z-score, but in most cases you don't know what it is, how do you calculate a z-score? You don't. You can't. So we're going to see, starting in the next chapter, how we get around that. Basically, we're going to see that we can calculate what's called a t-score rather than a z-score. And the t-score and the series of tests called t-tests will allow us to get around this problem of not knowing what that population standard deviation is. It doesn't require that we know it, okay? Which is usually a more realistic assumption in most cases. All right, so that's it then for chapter 15.